Section 11 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larissa Jaworski, Brisbane, Australia, March 2007. Familiar Letters on Chemistry by Justus Liebig. Letter 11. My dear Sir, in the immense yet limited expanse of the ocean, the animal and vegetable kingdoms are mutually dependent upon and successive to each other. The animals obtain their constituent elements from the plants, and restore them to the water in their original form when they are again serve as nourishment to a new generation of plants. The oxygen which marine animals withdraw in their respiration from the air, dissolved in sea water which is returned to the water by the vital processes of sea plants, that air is richer in oxygen than atmospheric air, containing 32 to 33%. Oxygen also combines with the products of the putrefaction of dead animal bodies, changes their carbon into carbonic acid, their hydrogen into water, and their nitrogen assumes again the form of ammonia. Thus we observe in the ocean a circulation takes place without the addition or subtraction of any element, unlimited in duration, although limited in extent, inasmuch as in a confined space the nourishment of plants exists in a limited quantity. We well know that marine plants cannot derive a supply of humus for their nourishment through their roots. Look at the great sea tang, the Fucus giganteus. This plant, according to Cook, reaches a height of 360 feet, and a single specimen, with its immense ramifications, nourishes thousands of marine animals. Yet its root is a small body no larger than a fist. What nourishment can this draw from a naked rock, upon the surface of which there is no perceptible change? It is quite obvious that these plants require only a hold, a fastening to prevent a change of place, as a counterpoise to their specific gravity, which is less than that of the medium in which they float. That medium provides the necessary nourishment and presents it to the surface of every part of the plant. Sea water contains not only carbonic acid and ammonia, but the alkaline and earthy phosphates and carbonates required by these plants for their growth, and which we always find as a constant constituent of their ashes. All experience demonstrates that the conditions of the existence of marine plants are the same which are essential to terrestrial plants, but the latter do not live like sea plants, in a medium which contains all their elements and surrounds with appropriate nourishment every part of their organs. On the contrary, they require two media, one of which, namely the soil, contains those elements which are absent from the medium surrounding them, i.e. the atmosphere. Is it possible that we could ever be in doubt respecting the office which the soil and its component parts subserve in the existence and growth of vegetables, that there should have been a time when the mineral elements of plants were not regarded as absolutely essential to their vitality? Has not the same circulation been observed on the surface of the earth which we have just contemplated in the ocean, the same incessant change, disturbance, and restitution of equilibrium? Experience in agriculture shows that the production of vegetables on a given surface increases with the supply of certain matters, originally parts of the soil which had been taken up from it by plants, the excrements of man and animals. These are nothing more than matters derived from vegetable food, which, in the vital processes of animals, or after their death, assumes again the form under which they originally existed, as parts of the soil. Now we know that the atmosphere contains none of these substances, and therefore can replace none, and we know that their removal from a soil destroys its fertility, which may be restored and increased by a new supply. It is possible, after so many decisive investigations into the origin of the elements of animals and vegetables, to the use of alkalis, of lime, and the phosphates, any doubt can exist as to the principles upon which a rational agriculture depends. Can the art of agriculture be based upon anything but the restitution of a disturbed equilibrium? Can it be imagined that any country, however rich and fertile, with a flourishing commerce, which for centuries exports its produce in the shape of grain and cattle, will maintain its fertility, if the same commerce does not restore in some form of manure those elements which have been removed from the soil, and which cannot be replaced by the atmosphere? Must not the same fate await every such country which has actually befallen the once prolific soil of Virginia, now in many parts no longer able to grow its former staple productions, wheat and tobacco? In the large towns of England, the produce both of English and foreign agriculture is largely consumed. Elements of the soil indispensable to plants do not return to the fields. Contrivances resulting from the manners and custom of the English people, and peculiar to them, render it difficult, perhaps impossible, to collect the enormous quantity of phosphates which are daily, as solid and liquid excrements, carried into the rivers. These phosphates, although present in the soil in the smallest quantity, are its most important mineral constituents. It was observed that many English fields exhausted in that manner immediately doubled their produce, as if by miracle, when dressed with bone earth imported from the continent. But if the export of bones from Germany is continued to the extent it has hitherto reached, our soil must be gradually exhausted, and the extent of our loss may be estimated by considering that 1 pound of bones contains as much phosphoric acid as 100 weight of grain. The imperfect knowledge of nature and the properties and relations of matter possessed by the alchemists gave rise, in their time, to an opinion that metals as well as plants could be produced from a seed. The regular forms and ramifications seen in crystals they imagined to be the leaves and branches of metal plants, and as they saw the seeds of plants grow, producing root, stem, and leaves, and again blossoms, fruit, and seed, apparently without receiving any supply of appropriate material, they deemed it worthy of zealous inquiry to discover the seed of gold, and the earth necessary for its development. If the metal seeds were once obtained, might not they entertain hopes of their growth? Such ideas could only be entertained when nothing was known of the atmosphere and its participation with the earth in administering to the vital processes of plants and animals. Modern chemistry indeed produces the elements of water, and combining them forms water anew. But it does not create those elements, it derives them from water. The new formed artificial water has been water before. Many of our farmers are like the alchemists of old. They are searching for the miraculous seed, the means which, without any further supply of nourishment to a soil scarcely rich enough to be sprinkled with indigenous plants, shall produce crops of grain 100-fold. The experience of centuries, nay thousands of years, is insufficient to guard men against these fallacies. Our only security from these and similar absurdities must be derived from a correct knowledge of scientific principles. In the first period of natural philosophy, organic life was supposed to be derived from water only. Afterwards it was admitted that certain elements derived from the air must be superadded to the water. But we now know that other elements must be supplied by the earth if plants are to thrive and multiply. The amount of materials contained in the atmosphere suited to the nourishment of plants is limited, but it must be abundantly sufficient to cover the whole surface of the earth with a rich vegetation. Under the tropics, and in those parts of our globe where the most genial conditions of fertility exist, a suitable soil, a moist atmosphere, and high temperature, vegetation is scarcely limited by space, and where the soil is wanting it is gradually supplied by the decaying leaves, bark, and branches of plants. It is obvious there is no deficiency of atmospheric nourishment for plants in those regions, nor are these wanting in our own cultivated fields. All that plants require for their development is conveyed to them by the incessant motions of the atmosphere. The air between the tropics contains no more than that of the Arctic zones, and yet how different is the amount of produce and equal surface of land in the two situations. This is easily explicable. All the plants of tropical climes, the oil and wax palms, the sugar cane, etc., contain only a small quantity of the elements of the blood necessary to the nutrition of animals, as compared with our cultivated plants. The tubers of the potato in Chile, its native country, where the plant resembles a shrub, if collected from an acre of land, would scarcely suffice to maintain an Irish family for a single day. Darwin. The result of cultivation in those plants which serve as food is to produce in them those constituents of the blood In the absence of the elements essential to these in the soil, starch, sugar, and woody fibre are perhaps formed, but no vegetable fibrine, albumin, or casein. If we intend to produce on a given surface of soil more of these latter matters than the plants can obtain from the atmosphere or receive from the soil of the same surface in its uncultivated and normal state, we must create an artificial atmosphere and add the needed elements to the soil. The nourishment which must be supplied in a given time to different plants in order to admit a free and unimpeded growth is very unequal. On pure sand, on calcareous soil, on naked rocks, only a few genera of plants prosper, and these are, for the most part, perennial plants. They require for their slow growth only such minute quantities of mineral substances as the soil can furnish, which may be totally barren for other species. Annual, and especially summer plants, grow and attain their perfection in a comparatively short time. They therefore do not prosper on a soil which is poor in those mineral substances necessary to their development. To attain a maximum in height in the short period of their existence, the nourishment contained in the atmosphere is not sufficient. If the end of cultivation is to be obtained, we must create in the soil an artificial atmosphere of carbonic acid and ammonia, and this surplus of nourishment, which the leaves cannot appropriate from the air, must be taken up by the corresponding organs, i.e. the roots, from the soil. But the ammonia, together with the carbonic acid, are alone insufficient to become part of a plant destined to the nourishment of animals. In the absence of the alkalis, the phosphates and other earthy salts, no vegetable fibrine, no vegetable casein can be formed. The phosphoric acid of the phosphate of lime, indispensable to the cerealia and other vegetables in the formation of their seeds, is separated as an excrement in great quantities by the rind and barks of ligneous plants. How different are the evergreen plants, the cacti, the mosses, the ferns, and the pines, from our annual grasses, the cerealia and leguminous vegetables. The former, at every time of the day during winter and summer, obtain carbon through their leaves by absorbing carbonic acid, which is not furnished by the barren soil on which they grow. Water is also absorbed and retained by their coriaceous or fleshy leaves with great force. They lose very little by evaporation compared with other plants. On the other hand, how very small is the quantity of mineral substances which they withdraw from the soil during their almost constant growth in a year, in comparison with the quantity which one crop of wheat of an equal weight receives in 3 months. It is by means of moisture that plants receive the necessary alkalis and salts from the soil. In dry summers a phenomenon is observed which, when the importance of mineral elements to the life of a plant was unknown, could not be explained. The leaves of plants first developed and perfected, and therefore nearer the surface of the soil, shrivel up and become yellow, lose their vitality, and fall off, while the plant is in an active state of growth, without any visible cause. This phenomenon is not seen in moist years, nor in evergreen plants, and but rarely in plants which have long and deep roots, nor is it seen in perennials in autumn and winter. The cause of this premature decay is now obvious. The perfectly developed leaves absorb continually carbonic acid and ammonia from the atmosphere, which are converted into elements of new leaves, buds, and shoots. But this metamorphosis cannot be effected without the aid of the alkalis and other mineral substances. If the soil is moist, the latter are continually supplied to an adequate amount, and the plant retains its lively green colour. But if this supply ceases from a want of moisture to dissolve mineral elements, a separation takes place in the plant itself. The mineral constituents of the juice are withdrawn from the leaves already formed, and are used for the formation of the young shoots, and as soon as the seeds are developed, the vitality of the leaves completely ceases. These withered leaves contain only minute traces of soluble salts, while the buds and shoots are very rich in them. On the other hand, it has been observed that where a soil is too highly impregnated with soluble saline materials, these are separated upon the surface of the leaves. This happens to culinary vegetables especially, whose leaves become covered in a white crust. In consequence of these exudations the plant sickens, its organic activity decreases, its growth is disturbed, and if this state continues long the plant dies. This is most frequently seen in foliaceous plants, the large surface of which evaporate considerable quantities of water. Carrots, pumpkins, peas, etc., are frequently thus diseased, when, after dry weather, the plant being near its full growth, the soil is moistened by short showers, followed again by dry weather. The rapid evaporation carries off the water absorbed by the root, and this leaves the salt in the plant in a far greater quantity than it can assimilate. These salts effloresce upon the surface of the leaves, and if they are herbaceous and juicy, produce an effect upon them as if they had been watered with a solution containing a greater quantity of salts than their organism can bear. Of two plants of the same species, this disease befalls that which is nearest its perfection. If one should have been planted later, or be more backwards in its development, the same external cause which destroys the one will contribute to the growth of the other. End of section 11.